Okay, this question is about a car that is moving at uh, speed v along a horizontal road, right? The engine exerts a force Fe while the car experiences a resistive force of R. Is very, very similar to the question one here, right? So let's draw the forces acting on the car, right? There should be four. Well, first one is the weight. You can draw it to the center of mass, somewhere near the middle. And then the reaction force from the ground will be from all the four views. You can actually represent them by a single force from the ground upwards, acting upwards on the all the four views combined together. So it's a normal reaction. Okay, I draw it slightly separated um, from the W here, but they actually you can take them to be aligned to each other and but in opposite direction. Then there is this force that is due to the engine in the forward direction. Okay, I can draw it in this way. Force acting in the forward direction, Fe, generated by the engine through the wheels and pressed onto the road that push the car forward. And then there is a resistance force in the opposite direction. This resistance force is due to air and friction on the non-driving wheel of the car. So this is a total resistance in the reverse direction. Okay, opposing the motion of the car. The car is moving with speed v forward, right? So this is normally how the forces are. Now, in general, the forces that we are interested will be the one that is in the horizontal direction, because the car doesn't move off the surface road. It doesn't move in a vertical direction. So most of the time, you'll be only interested in the uh, forces in the horizontal direction. Okay. So first part B here, it is speed v is constant. V is constant means a equals 0. The horizontal acceleration is 0 horizontally. Maybe I call it horizontal. A is 0. So therefore the horizontal force must be equal in magnitude. So Fe minus R equals 0. Minus R equals to MA, and X equals 0. It's in the horizontal direction. So Fe equals to R. Okay. So that's the in a vertical direction, of course, the vertical direction, the n will always be equal to W in magnitude. Okay, and x equal to mg. Okay, so there's no motion in the vertical direction. There's nothing interesting happening there in the vertical direction. Right. Determine the maximum power exerted by a car to travel at constant speed. The power is represented by the product of force uh, of the engine multiplied by the speed, because the speed here is the constant speed here is v. The speed doesn't increase anymore. It's already traveling at its maximum speed, so therefore the power is maximum. And since Fe equals to R here in the above, Fe equals to R, so you can also represent answer can also be written as RV. So it's either Fe times V or R times V. Okay. In the vertical, of course, thing is happening here, so you don't have to worry about the forces from the vertical. Right. Next, the driver steps on the accelerator and the car now starts to accelerate. Right. There's a now acceleration not zero anymore. It's some a value here. So what is the new force exerted uh, by the engine to sustain the acceleration? Now, whenever there's an acceleration, you need to go back to Newton's second law. So net force equals to mass times acceleration. The net force now, the Fe, the new Fe, yeah, new Fe, new F, new engine force, minus R equals to mass times acceleration. So the new engine force equals to R plus ma. Okay, so this is the larger value now. It's larger than before. So this is the new engine force in the horizontal direction. determine the maximum power at this instant. It should be at this instant, because when you accelerate, the velocity is expected to increase, right? So you may want to add this question to the question at this instant. So the power increase as the velocity of the car gets higher and higher. So what we are calculating now is the power exerted by the engine at this instant when it's being accelerated. So the new power, the new power is I say new here is compared to this one. When you press on the accelerator, the new power is the new force now multiplied by the speed at the instant. We haven't quite accelerated yet, so it's R plus ma. Okay, so times v. Now this answer definitely is greater than the power that is used in the before the acceleration. Okay, so this new when you press on the accelerator, you need to exert a larger force, therefore a greater power is provided by the engine. Right, now we make things a bit challenging. We move the car up an incline with the angle beta. It still move with a constant speed, now. Resistive force remains the same as before. Okay, so the value is still R. Just to remember R, the capital R here. Right, so we are okay with this diagram here. Same as before, draw all the forces acting on the car. Similar to before, now we have mg, and the normal reaction is now perpendicular to the surface, so we can draw it this way, perpendicular, and there's an engine force driving it parallel to the inclined plane, Fe, and the resistive force is also against the velocity direction, so there's R here. Okay, so the main difference is that now the surface is inclined, so the weight still remain in the vertical direction. Everything else is either pointing along the direction of the plane or perpendicular to the direction of the plane. Right, determine the forces exerted by engine to maintain constant motion at a speed. So let's look at the parallel to the plane, direction parallel to the plane here. So there's no acceleration. It means that okay, we have to resolve the forces that are not parallel to the plane. So let me just use a different color here. So the only odd one is mg. Actually, mg is the one that is has some component parallel to plane, some component perpendicular to plane. So you remember in the previous chapter on dynamics here, the mg can resolve into two components. One component perpendicular to the plane, which is mg cosine theta, and then the other component is parallel to the plane, which is mg sine theta. Okay, if you are not sure, can you go back to the previous chapter to revise on this thing here? So we have we have this two components due to the mg, parallel to the plane downwards mg sine theta, perpendicular to the plane in the downward direction, opposite to the end is mg cosine theta. We are interested more in the component is parallel to the plane. So if you write the equation using Newton's second law, because constant speed means acceleration equals zero, so the net force in the parallel to plane will be the force due to the engine, okay, minus weight R minus weight mg sine theta, and equals to ma. A is 0, of course, m times 0, so everything goes to 0. So the equation is simply engine force is r plus mg sine theta. Okay, now in the direction that is perpendicular to the plane, there's nothing interesting here, because what happens is n will cancel out, minus mg cos theta equals 0. So these two are actually equal and opposite. They are not action reaction pair, but they're equal and opposite. So there's no acceleration in the direction perpendicular to the plane, right? So that's part 2 here. Right. Now, what happens if, similar to the previous question, the driver steps on the accelerator and there's an acceleration. So again, we continue from this equation here. All right, continue from there. So similar. Okay, this one should be beta instead of it should be beta. So let me just do the correction here. This one should be beta. Uh, it should be beta. Should be beta. This should be beta. Okay, I'm so used to theta here, so it should be beta here. Okay, so all my previous part here should be beta. Okay, it should be beta. I was so used to theta. Okay, right. So let's go back to part 3 here. It's actually very similar to the part 2 here. So writing instead of writing a equals 0, now we have some value of a which is not 0. Okay, so when we write it out, the FE, the new FE now, I call it new engine force. New engine force now is R plus mg sine beta, sorry, again my mistake, plus ma. So this is a new engine force. In the vertical direction, in a perpendicular to the plane, is nothing that is interesting here. So again, the same kind of method is used. We just apply Newton's second law, can work out the new engine force. And then what's the power at this instant of time? The power at this instant of time is simply the product of the new power. The new power at this time is simply the new engine force multiplied by uh, the, the new speed. Okay, at this instant. In this case, haven't acquired new speed yet. So we just replace the force by the whole term mg sine beta plus ma. Okay, so next all for this question here.